Tonight, we're going to witness the end of everything we know. Not from some cosmic disaster or sudden catastrophe, but from something far more inevitable, far more certain. Right now, at this very moment, an entire galaxy containing 1 trillion stars is racing toward us at 250,000 miles per hour. In roughly 4 billion years, Andromeda will arrive, and when it does, the Milky Way as we know it will cease to exist. The night sky will be transformed beyond recognition. Our solar system, if it survives, will be hurled into a completely different region of space, and everything, absolutely everything, about our cosmic home will be rewritten. By the end of tonight, you're going to understand exactly how this collision unfolds, what it means for Earth, what happens to our Sun, and what strange new galaxy emerges from the merger. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Right now, somewhere around 2.5 million light-years away, Andromeda sits in the night sky. You can see it with your naked eye if you know where to look, and you're far from city lights. It appears as a small, fuzzy patch in the constellation Andromeda, nothing particularly dramatic. Most people who see it don't realize they're looking at an entire galaxy containing 1 trillion stars, more than twice as many stars as our Milky Way. And they certainly don't realize that galaxy is falling straight toward us. Let's put that distance in perspective for a moment. 2.5 million light-years means that the light you see when you look at Andromeda left that galaxy 2.5 million years ago. Back when that light began its journey, modern humans didn't exist yet. Homo erectus was still the dominant human species on Earth. The Stone Age was in full swing. No cities, no agriculture, no writing, no civilization. And that light has been traveling through space at 186,000 miles per second this entire time, crossing the incomprehensible void between the galaxies. The closure speed is roughly 250,000 miles per hour. That might sound incredibly fast, and by everyday standards it is. A commercial jet travels at maybe 500 miles per hour. The International Space Station orbits Earth at about 17,500 miles per hour. The fastest spacecraft ever built, the Parker Solar Probe, reached speeds of roughly 400 to 30,000 miles per hour as it dove close to the Sun. Andromeda is approaching at speeds comparable to our fastest spacecraft. But it's not a tiny probe. It's an entire galaxy containing 1 trillion stars. But when you're starting from 2.5 million light-years away, even at 250,000 miles per hour, it takes a very, very long time to close that distance. We're talking about a distance so vast, it's almost impossible to comprehend. If you could somehow drive to Andromeda at highway speed, the trip would take hundreds of trillions of years. Even at Andromeda's current closing speed of 250,000 miles per hour, which is faster than any spacecraft we've ever built, it still takes billions of years to cover the distance. But that's assuming constant velocity and ignoring gravitational acceleration, which becomes more significant as the galaxies get closer. When you account for gravity pulling them together faster and faster, the collision happens in approximately 4 billion years. 4 billion years before the outer edges of these two galaxies begin to overlap. To put that timescale in perspective, 4 billion years ago, Earth was only about 600 million years old. The Moon had just finished forming from the debris of a massive impact. The surface was still cooling from its molten state. Life hadn't even begun yet. There were no cells, no bacteria, nothing alive at all. Everything that has happened on Earth since then, every organism that ever lived, every species that evolved and went extinct, all of human history, from the first stirrings of life in ancient oceans to the present day, All of that has unfolded in less time than it will take for Andromeda to reach us. So when we talk about this collision, we're not talking about something that's going to happen next year, or in your lifetime, or even in a million years. We're talking about something so far in the future that it's almost beyond comprehension. But it is going to happen. The physics are absolutely certain. Andromeda is coming, and when it arrives, everything changes. Before we dive into the collision itself, we need to understand what's actually going to collide. Our Milky Way is what astronomers call a barred spiral galaxy. Imagine a flat disk, roughly 100,000 light-years across, with elegant spiral arms curving outward from the center. At the very core sits a bar-shaped structure made of densely packed stars, and at the heart of that bar lurks a supermassive black hole weighing approximately 4 million times the mass of our Sun. This black hole is called Sagittarius A star, and while it's incredibly massive by everyday standards, it's actually relatively modest for a galactic black hole. Let's break down the structure of the Milky Way in more detail, because understanding this will help us understand what happens during the collision. The central bulge, the densely packed region at the very core, contains about 10 billion stars crammed into a relatively small volume. If you could somehow stand on a planet near the galactic center, the night sky would be ablaze with stars. Thousands of stars would be visible to the naked eye, far more than the few thousand we can see from Earth. The brightest stars would cast shadows. True darkness would be almost impossible to find. The bar structure extends outward from the bulge, spanning roughly 27,000 light-years from end to end. This bar is thought to be a relatively recent development in the Milky Way's history, forming perhaps 2 billion to 3 billion years ago. Not all spiral galaxies have bars, but roughly 2/3 of nearby spiral galaxies do. The bar acts like a cosmic highway, funneling gas from the outer galaxy toward the center, feeding star formation in the central regions. Then come the spiral arms, those graceful curves that give spiral galaxies their distinctive appearance. The Milky Way has two major spiral arms, called the Scutum Centaurus arm and the Perseus arm, plus several minor arms. These arms aren't solid structures, they're density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. Think of them like traffic jams on a highway. The cars aren't always the same. They enter the jam, slow down, then speed up and exit the other side. But the jam itself persists, moving slowly around the loop. Our Sun sits in a minor arm called the Orion Spur, positioned between two major arms. We're about 26,000 light-years from the galactic center, roughly halfway out toward the edge. From our vantage point, we can see the Milky Way as a band of light crossing the sky, but we're seeing it from inside, which makes it hard to determine the overall structure. The Milky Way contains somewhere between 100 billion and 400 billion stars. That's an enormous range, but counting stars when you're inside the galaxy is extraordinarily difficult. It's like trying to count all the trees in a massive forest while standing in the middle of it. Everything nearby blocks your view of what's farther away. Dust lanes obscure entire regions. The galactic center is completely hidden behind clouds of gas and debris when viewed in visible light. Infrared telescopes can peer through the dust, and radio telescopes can detect emissions from gas clouds, but getting an exact count remains challenging. Most of these stars are small, cool, red dwarf stars. Red dwarfs make up roughly 70 to 80% of all stars, but they're so dim that we can't see any of them with our naked eyes, even though many are relatively nearby. The brightest star in our night sky, Sirius, is a white star about 6 light-years away, and roughly 25 times more luminous than the Sun. But there are dozens of red dwarfs closer than Sirius that we can't see without telescopes because they're just too dim. The Sun orbits the galactic center at approximately 514,000 miles per hour. Even at this enormous speed, it takes about 225 million to 250 million years to complete one orbit. That's called one galactic year, or cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 to 21 orbits around the galaxy, 20 trips around this enormous cosmic carousel. During each orbit, the Sun passes through the spiral arms multiple times. When we're inside an arm, the local density of stars and gas is higher, which might increase the rate of comet impacts on planets or expose us to nearby supernova explosions. When we're between arms, like we are now, things are calmer and safer. Some researchers have speculated that mass extinctions on Earth might be correlated with passages through spiral arms, but the evidence is ambiguous at best. The visible disk of the Milky Way, all those stars we can see, is embedded in a much larger halo of dark matter. This dark matter halo extends perhaps 600,000 light-years from the galactic center, 6 times farther than the visible disk. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. But we know it's there because of its gravitational effects. The outer stars in the galaxy orbit faster than they should based on the visible matter alone. The extra gravity holding them in their orbits must come from dark matter. In total, the Milky Way probably weighs somewhere between 1 trillion and 1.5 trillion times the mass of the Sun. Most of that mass, roughly 85 to 90%, is dark matter. Only about 10 to 15% is normal matter, the atoms that make up stars, planets, gas, clouds, and us. Now, Andromeda is similar in structure, but considerably larger. It's also a spiral galaxy, though its spiral arms are wound more tightly than ours. It spans roughly 220,000 light-years across, more than twice the diameter of the Milky Way. And it contains approximately 1 trillion stars. That's at least twice as many stars as we have, possibly 3 times as many. Andromeda's central bulge is more massive and more extended than ours. It contains perhaps 20 billion to 30 billion stars, 2 to 3 times more than the Milky Way's bulge. This gives Andromeda a brighter, more prominent core when viewed through telescopes. Andromeda's supermassive black hole is much more massive than ours, weighing in at roughly 100 million to 200 million solar masses. The exact mass is uncertain because measuring black hole masses at such distances is difficult, but even the lower estimate makes it about 25 times heavier than Sagittarius A star. The upper estimate makes it 50 times heavier. This black hole sits at the center of Andromeda, surrounded by a dense cluster of stars orbiting at tremendous speeds. If you could zoom in close enough, you'd see stars completing orbits around the black hole in just a few years, moving at speeds of thousands of miles per second. Andromeda also has a more active recent history of star formation than the Milky Way. In the past few billion years, Andromeda has experienced bursts of intense star formation, possibly triggered by mergers with smaller galaxies. You can see evidence of this in the blue stars scattered through Andromeda's disk, young hot stars that have formed relatively recently. Both galaxies are part of what astronomers call the local group, a collection of about 80 galaxies bound together by gravity. The local group spans about 10 million light-years across, though most of that volume is empty space. The member galaxies are scattered throughout this volume, loosely bound by their mutual gravitational attraction. Most of the member galaxies are small, dwarf galaxies containing only millions or billions of stars. The Large Magellanic Cloud and Small Magellanic Cloud, 2 dwarf galaxies orbiting the Milky Way, are visible from the southern hemisphere as fuzzy patches in the night sky. The Large Magellanic Cloud contains maybe 30 billion stars, the Small Magellanic Cloud perhaps 3 billion stars. These are substantial galaxies by dwarf standards, but tiny compared to the Milky Way or Andromeda. There are dozens of even smaller dwarf galaxies, some containing fewer than 1 million stars, scattered throughout the local group. Many of these are satellite galaxies, orbiting either the Milky Way or Andromeda. We've discovered new dwarf galaxies orbiting the Milky Way as recently as the past decade, and there are probably more we haven't found yet because they're so faint and small. The Milky Way and Andromeda are by far the two largest members of the local group. Together, they dominate the gravitational dynamics of the entire group. The third largest member is the Triangulum Galaxy, a spiral galaxy containing perhaps 40 billion stars, but even Triangulum is dwarfed by the two giants. For billions of years, these two giant galaxies have been orbiting around their common center of mass, but they're not in stable orbits. They're falling toward each other. Gravity is pulling them together inexorably. And unlike planets orbiting a star, which can maintain stable orbits indefinitely if nothing disturbs them, galaxies on a collision course like this don't have enough angular momentum to avoid eventually merging. They're doomed to collide. The center of mass of the Milky Way Andromeda system sits somewhere between the two galaxies, closer to Andromeda because Andromeda is more massive. Both galaxies are falling toward this point, though Andromeda has less far to fall because it's already closer to the center of mass. As they fall, they're also moving sideways to some degree, which is why the collision won't be perfectly head-on. They'll hit at an angle, with their disks tilted relative to each other. This angle adds complexity to the merger, affecting how the spiral arms get disrupted and how the final merged galaxy takes shape. So how do we know all this? How do astronomers determine that Andromeda is moving toward us, and how do they calculate the timing of the collision? The answer involves some sophisticated observations and measurements. First, astronomers measure what's called the radial velocity, how fast an object is moving directly toward or away from us. This is done using something called the Doppler effect. You're familiar with the Doppler effect from sound. When an ambulance drives toward you, its siren sounds higher pitched because the sound waves are compressed. When it drives away, the siren sounds lower because the waves are stretched out. Light works the same way. If an object is moving toward you, its light waves are compressed toward the blue end of the spectrum. If it's moving away, they're stretched toward the red end. When astronomers observe the spectrum of light from Andromeda, they look at specific wavelengths emitted by hydrogen and other elements. These wavelengths are shifted toward the blue end of the spectrum. That means Andromeda is moving toward us. By measuring exactly how much the wavelengths are shifted, they can calculate the velocity. The answer is roughly 250,000 miles per hour. But that's just the velocity along our line of sight. Galaxies can also have sideways motion, called proper motion. Measuring proper motion is much harder because you're trying to detect tiny shifts in position on the sky. For something as distant as Andromeda, this requires incredibly precise measurements over many years. The Hubble Space Telescope has been observing Andromeda for decades, carefully measuring the positions of stars within the galaxy and tracking how those positions change over time. From these measurements, astronomers have determined that Andromeda's sideways motion is relatively small. It's coming almost directly toward us, with only a slight angle. Once you know the velocity and direction, you can predict when the collision will happen. It's simple kinematics at that point. You know the current distance, roughly 2.5 million light-years. You know the approach velocity, roughly 250,000 miles per hour. Divide distance by velocity, and you get time. The answer comes out to roughly 4 billion years, give or take a few 100 million years. The uncertainty exists because we don't know the exact masses and positions perfectly, and small gravitational interactions with other members of the local group introduce some unpredictability. But the order of magnitude is solid. 4 billion years from now, these two galaxies will begin to merge. Now, before we go any further, we need to address a common misconception. When people hear galaxy collision, they often imagine something violent and catastrophic, like two cars smashing together at high speed. They picture stars exploding, planets being destroyed, chaos and destruction on a cosmic scale. That's not what happens. In fact, the reality is far stranger and in some ways far less dramatic than most people expect. Here's the key fact that changes everything. Space is mostly empty. Profoundly, almost incomprehensibly empty. Even inside a galaxy where stars are relatively concentrated, the distances between stars are absolutely enormous compared to the sizes of the stars themselves. Let's quantify this with some specific examples. Our nearest stellar neighbor, Proxima Centauri, sits about 24 light-years away. That's roughly 25 trillion miles. The Sun has a diameter of about 864,000 miles. Proxima Centauri is a red dwarf, smaller than the Sun, with a diameter of maybe 120,000 miles. So we have two objects, the Sun and Proxima Centauri, with diameters measured in hundreds of thousands of miles, separated by a distance of 25 trillion miles. That's a ratio of roughly 30 million to 1. The distance is 30 million times larger than the size of the objects. To get a sense of this scale, imagine the Sun as a basketball, roughly 12 inches in diameter. On that scale, Proxima Centauri would be a tennis ball about 5 inches in diameter, and the distance between them would be approximately 4,000 miles. That's the distance from New York to London, or from Los Angeles to Tokyo. Two balls, one basketball-sized and one tennis ball-sized, separated by the width of an entire ocean. Now scale back up to the real universe. The space between the Sun and Proxima Centauri is empty, except for an extremely diffuse scattering of hydrogen atoms, maybe 1 atom per cubic centimeter, and the occasional dust grain. The nearest star after Proxima Centauri is Alpha Centauri A, about 37 light-years away. Then comes Barnard's star at about 6 light-years, Wolf 359 at 9 light-years, Lalande 21185 at 3 light-years, Sirius at 6 light-years. Within 10 light-years of the Sun, there are only about a dozen star systems. Within 20 light-years, there are roughly 130 known star systems, though this number keeps growing as we discover more dim red dwarfs and brown dwarfs that were previously too faint to detect. This is what we mean when we say space is empty. The stars are scattered through an enormous volume with vast distances between them. Each star is like an isolated lighthouse in an ocean of darkness, separated from its nearest neighbors by distances millions of times larger than the stars themselves. So when two galaxies collide, the vast majority of stars simply pass by each other with enormous amounts of space between them. Imagine two swarms of bees flying through each other. If the bees are far enough apart, the two swarms can interpenetrate without any collisions between individual bees. That's roughly what happens when galaxies merge. Direct collisions between stars are extraordinarily rare. In fact, during the entire merger of the Milky Way and Andromeda, astronomers estimate that maybe a few hundred stars might actually collide out of hundreds of billions. The probability that any given star, including our Sun, will collide with another star is essentially zero. You could calculate it precisely, and you'd get a number like 1 in 10 billion or 1 in 100 billion. Vanishingly small. To understand why collisions are so rare, consider what has to happen for two stars to collide. They need to be moving toward each other. They need to be aimed directly at each other to within the width of a star, and they need to be in the right place at the right time as their orbits bring them together. Stars in a galaxy are moving in orbits around the galactic center, not randomly, so there's some organization to their motions. During the merger, this organization breaks down and motions become more chaotic. But even with chaotic motions, the volume of space is so large and the stars are so small that collisions remain extremely unlikely. Let's do a back-of-the-envelope calculation. The Milky Way and Andromeda together contain perhaps 1.5 trillion stars. Assume an average star has a diameter equal to the Sun's diameter, about 864,000 miles. The total cross-sectional area of all these stars is approximately 1.5 trillion times pi times 432,000 miles squared. That works out to roughly 880 quadrillion square miles. Now consider the volume through which these stars are moving. The collision region is roughly the size of both galaxies combined, maybe 300,000 light-years across and 10,000 light-years thick at the disk. Converting to miles and calculating volume, we get something on the order of 10 to the 54th power cubic miles. The stars spend maybe 1 billion years passing through each other during the multiple passages of the merger. A star moving at typical galactic velocities, say 400,000 miles per hour, covers about 3.5 billion miles in that time, sweeping out a volume, like a cylinder, with length 3.5 billion miles and radius 432,000 miles. The volume swept out by one star is roughly 1.6 sextillion cubic miles. Multiply by 1.5 trillion stars, and you get the total volume swept out by all stars, roughly 2,500 nonillion cubic miles. Compare this to the total volume of the collision region, 10 to the 54th power cubic miles, and you find that stars sweep out only a tiny fraction of the available space, maybe 1/10,000,000th or less. This is why collisions are so rare. The stars collectively fill only a tiny fraction of the space available to them. Even with 1.5 trillion stars moving around for 1 billion years, most of the volume remains empty. And most stars never come anywhere close to hitting another star. But that doesn't mean nothing happens. Far from it. The collision might not be violent in the sense of physical impacts, but it's absolutely transformative in terms of gravitational effects. When two galaxies merge, their gravitational fields interact in complex ways. Every star in one galaxy feels the gravitational pull from every star in the other galaxy, plus the pull from all the dark matter in both galaxies, plus the pull from the gas clouds. These combined gravitational forces create a complex, time-varying field that changes as the galaxies move through and around each other. Stars that were peacefully orbiting the galactic center in stable, circular orbits suddenly find themselves pulled in new directions. A star on the near side of one galaxy, the side facing the other galaxy, gets pulled more strongly toward the other galaxy than a star farther away. This differential pull, called a tidal force, stretches the galaxy. As the galaxies interpenetrate, stars experience gravitational kicks. A star might be moving in one direction, then pass near a concentration of mass in the other galaxy and get deflected into a different direction. Or it might speed up or slow down depending on the direction and strength of the gravitational pull. Orbits that were stable for billions of years become chaotic. Some stars get accelerated, gaining energy and moving into wider, more elliptical orbits. Others get decelerated, losing energy and falling into tighter orbits. Some get flung outward toward the edges of the merging system, or even ejected entirely, escaping into intergalactic space. Others get pulled inward toward the center, where they contribute to building up the dense core of the merged galaxy. The entire structure of both galaxies gets scrambled and reorganized. The neat spiral arms that existed before the collision get torn apart by tidal forces. The organized, Coherent rotation that maintained those spiral arms breaks down as stars are kicked into different orbits with different inclinations and eccentricities. Computer simulations of galaxy mergers run on powerful supercomputers show this process in detail. Astronomers create simulations with millions of particles, each one representing a clump of stars or dark matter, and calculate the gravitational forces between all the particles at each time step. Running these simulations forward in time, you can watch the galaxies approach, interpenetrate, separate, come back together, and eventually merge. The simulations show that after the merger, the resulting galaxy no longer looks like a spiral. It looks like an elliptical galaxy, a rough sphere or football shape with no spiral arms, no disk structure, and stars moving in random orbits rather than organized rotation. And then there's the gas. Galaxies aren't just stars. They also contain vast clouds of gas and dust floating in the space between stars. This gas is mostly hydrogen, the simplest and most abundant element in the universe, along with some helium and traces of heavier elements. The gas is much more diffuse than stars, typically only 1 atom per cubic centimeter in the disk of a galaxy like the Milky Way. That's far less dense than the best laboratory vacuum we can create on Earth. But it's spread out over enormous volumes, so the total mass adds up. The Milky Way contains perhaps 10 billion to 15 billion solar masses of gas, roughly 10% of the total visible mass. This gas is crucial for star formation. Stars form when gas clouds collapse under their own gravity, becoming denser and hotter until nuclear fusion ignites in their cores. The gas in galaxies is the raw material from which new generations of stars are born. Unlike stars, which are so small and far apart that they almost never collide, gas clouds occupy large volumes and they do interact. Gas clouds can be thousands or even millions of light years across, spanning significant fractions of a galaxy's disk. When two galaxies collide, their gas clouds inevitably run into each other. When two gas clouds slam into each other at hundreds of thousands of miles per hour, what happens? The kinetic energy of the collision, the energy of motion, gets converted into thermal energy, heat. The gas heats up dramatically, reaching temperatures of millions of degrees in the collision zone. Hot gas glows. At temperatures of millions of degrees, hydrogen atoms become ionized, stripped of their electrons, and the ionized gas emits X-rays and ultraviolet light. This makes the collision regions visible to telescopes that can observe these wavelengths. But something else happens too. The collision compresses the gas. Gas that was spread out over a large volume gets squeezed into a smaller volume, increasing its density. And when gas gets compressed to high enough density, gravity can take over. If a region of gas is dense enough and cool enough, its own gravity can overcome the thermal pressure that would otherwise make it expand. The gas starts to collapse, falling in on itself under its own weight. As it collapses, it fragments into clumps, and these clumps continue to collapse until they're dense enough and hot enough for nuclear fusion to begin. At that point, they become stars. This process is called a starburst. Galaxy mergers trigger intense episodes of star formation, creating millions of new stars over a relatively short period, just a few 100 million years. That's short by cosmic standards, though still enormously long by human standards. These newborn stars are different from most of the existing stars in the galaxies, because they're forming from gas that's been compressed and heated by the collision. And because the conditions favor the formation of massive stars, many of the stars born in starbursts are huge, tens or even hundreds of times the mass of the Sun. Massive stars burn incredibly hot and bright. They're blue or blue-white in color because their surface temperatures exceed 20,000 or 30,000 degrees, compared to the Sun's surface temperature of about 10,000 degrees. They pump out enormous amounts of energy, thousands or tens of thousands of times more luminous than the sun. But massive stars live fast and die young. Because they're burning through their fuel so quickly, they exhaust their nuclear fuel in just a few million years. Compare that to the sun, which will burn for about 10 billion years total. A star 20 times the mass of the sun might live only 10 million years. A star 50 times the sun's mass might live only 3 million to 4 million years. When these massive stars run out of fuel, they don't fade away gently. They explode, catastrophically, violently, in what's called a core collapse supernova. The star's core implodes, then rebounds, sending a shockwave outward that blows the star apart. For a few weeks, the exploding star shines as brightly as an entire galaxy, radiating more energy than the sun will emit over its entire 10 billion year lifetime. So the galaxy merger triggers not just star formation, but also a dramatic increase in the supernova rate. Instead of 1 or 2 supernovae per century, which is typical for a normal spiral galaxy like the Milky Way, a merging galaxy might experience dozens or hundreds of supernovae per century during the peak of the starburst. Supernovae are powerful events with consequences that extend far beyond the exploding star itself. They produce high-energy radiation, gamma rays and X-rays, that can sterilize nearby regions of space. They create shock waves that propagate through the surrounding gas, compressing it and potentially triggering more star formation. They produce cosmic rays, high-energy particles, mostly protons traveling at nearly the speed of light. These cosmic rays spread throughout the galaxy, and if you're anywhere near a supernova when it explodes, the radiation can be dangerous. Within maybe 100 light-years or so, the radiation could strip away a planet's ozone layer, exposing the surface to harmful ultraviolet light from the star. It could cause mutations in any life that exists. It could potentially trigger mass extinctions if the radiation is intense enough. During the starburst phase of the merger, any planets in the wrong place at the wrong time could be bathed in this radiation. This is one reason why life during the merger would be challenging, even if your planet's orbit remains stable and your star doesn't have any close encounters with other stars. The increased supernova rate creates a more hazardous radiation environment throughout the merging galaxies. Let's walk through what actually happens, step by step, starting from today and moving forward through time. We'll take it slow, because this process unfolds over billions of years and there are many distinct phases, each with its own character and consequences. Right now, today, Andromeda appears as a small smudge in our night sky. From a dark location, away from light pollution, on a moonless night, you can see it with your naked eye. It's faint, just barely visible, located in the constellation Andromeda, northeast of the Great Square of Pegasus. Most people who see it don't recognize it as anything special, just a faint, fuzzy patch among thousands of visible stars. Through a telescope, you can see its spiral structure, the bright core surrounded by dimmer spiral arms. Through large telescopes, and with long exposure photographs, astronomers can photograph it in exquisite detail. Modern images reveal billions of individual stars, especially in the outer regions, where they're not overwhelmed by the central glow. You can see nebulae where new stars are forming, glowing clouds of gas ionized by the radiation from hot young stars. And you can see dark dust lanes threading through the spiral arms, silhouetted against the background glow. Andromeda is moving across our sky incredibly slowly. Its proper motion, the sideways movement as seen from Earth, is measured in milliarcseconds per year. That's thousandths of an arcsecond, where an arcsecond is 1/3600th of a degree. Even with our most precise instruments, tracking this motion requires observations spanning many years. The Hubble Space Telescope and Gaia satellite have measured Andromeda's proper motion precisely determining that it's moving almost directly toward us, with only a slight sideways component. Over the next 100 million years, very little changes from a visual perspective. 100 million years is an enormous span of time by human standards, longer than the entire age of the dinosaurs. But on cosmic scales, it's just a blink, less than 1% of the Milky Way's age. During this time, Andromeda gets closer by roughly 25,000 light-years, about 1/4 of the Milky Way's diameter. But since it started 2.5 million light-years away, this represents less than 1% of the total distance. From Earth, Andromeda would appear perhaps 1% larger, an increase too small to notice without precise measurements. But astronomers living during this time, assuming human civilization or its successors still exist, would be watching carefully. They'd have detailed predictions of the collision, refined over millennia of observations. They'd be tracking Andromeda's position and velocity with extraordinary precision. They'd be studying the structure of both galaxies in detail, cataloging millions or billions of stars, mapping the distribution of gas and dark matter. As we move forward another 500 million years, now 600 million years from today, Andromeda has closed perhaps 150,000 light-years, about 6% of the original distance. Still not much change to the naked eye. Andromeda might appear maybe 5 to 6% larger, but without side-by-side comparisons, you wouldn't notice. But gravitationally, subtle effects are beginning. At distances of under 2 million light-years, the gravitational pull between the two galaxies is becoming more significant. It's still weak compared to the internal gravity holding each galaxy together, but it's there, and it's growing stronger as the distance decreases. This gravitational interaction begins to affect the outer parts of both galaxies. Stars in the outermost regions, where they're only weakly bound to their parent galaxy, start to feel the pull from the other galaxy. Their orbits begin to change subtly, stretching and distorting. As we jump forward another billion years, now 1.6 billion years from today, things are beginning to look noticeably different. Andromeda has closed roughly 40% of the distance and now sits perhaps 1.5 million light-years away. It's noticeably larger in our sky, maybe 50 to 60% bigger than it appears today. Through a telescope, you can start to see hints of distortion in its outer regions. The gravitational interaction is now strong enough to begin pulling tidal tails from both galaxies. These are long, thin streams of stars being pulled out by the differential gravitational forces, the tidal effects we discussed earlier. They're still subtle, just slight distortions in the outer edges of each galaxy, but they're there and they're growing. Let's jump forward another 1.5 billion years, bringing us to 3 billion years from today. Andromeda is now dramatically closer, perhaps under 1 million light-years away, less than half the original distance. It's grown significantly in our sky, now covering an area maybe 3 to 4 times larger than today. Through a telescope or binoculars, its spiral structure is clearly visible, the bright central bulge surrounded by sweeping spiral arms. You can see individual bright stars within Andromeda, the blue supergiants and red supergiants, stars so luminous they're visible even across this vast distance. The tidal tails are now prominent, clearly visible features, stretching perhaps 100,000 light-years or more from each galaxy. One tail points roughly toward the other galaxy, pulled out by the stronger gravitational attraction on the near side. The other tail points away, lagging behind as the far side feels less pull. At this stage, astronomers would have refined their predictions immensely. They'd have detailed maps of both galaxies, tracking billions of individual stars. Computer simulations would predict exactly how the merger will proceed, where the first contact will occur, which regions will experience the most dramatic effects. These simulations would be running on computers far more powerful than anything we have today, possibly quantum computers or other exotic technologies. They'd be modeling not just the stars, but also the gas, the dark matter, even potentially the magnetic fields threading through the galaxies. The civilization living during this era, if any exists, would be preparing. If they're confined to planets, they might be building shelters or habitats that could withstand increased radiation. If they're spacefaring, they might be relocating populations away from regions expected to be most affected by the merger. Inside both galaxies, things are beginning to change more noticeably. The Sun's orbit around the galactic center, stable for billions of years, is starting to feel effects from Andromeda's gravity. The orbit might be becoming slightly more elliptical, slightly more tilted relative to the galactic disk. These changes are small, but they're real and measurable. The gas clouds in both galaxies are beginning to be affected more dramatically. Unlike stars, which are point masses responding only to gravity, gas clouds can be compressed and stretched by pressure waves, magnetic fields, and radiation. As the galaxy's gravitational fields begin to overlap, ripples propagate through the gas, compressing some regions and rarefying others. Some of these compressed regions might collapse and form stars, triggering localized bursts of star formation even before the actual collision. These early warning signs, pre-merger starbursts, have been observed in some interacting galaxies in the distant universe, confirming that the process begins long before the galaxies actually overlap. Now let's jump forward another billion years, bringing us to 4 billion years from today. This is it, first contact. The moment we've been building toward. Andromeda now dominates the night sky. Instead of appearing as a small object, it stretches across a huge swath of sky, maybe 20 or 30 times the width of the full moon. That's roughly 10 to 15 degrees across, about the span of your outstretched hand at arm's length. You can see incredible detail with your naked eye, the bright central bulge, the spiral arms, regions of bright blue star formation where young massive stars have recently formed. The dark dust lanes threading through the disk are visible, silhouetted against the background glow, and it's growing larger every year, noticeably so. If you could watch a time-lapse spanning a human lifetime, you'd see Andromeda slowly expanding across the sky, the details becoming sharper and more prominent. From our perspective, looking up at this approaching giant, the sight would be simultaneously beautiful and terrifying. Beautiful because of the sheer scale and complexity of the structure, the billions of stars arranged in sweeping spiral patterns. Terrifying because this massive object is coming straight at us, and there's nothing anyone can do to stop it. The tidal tails are now enormous, stretching for hundreds of thousands of light years. They're clearly visible in the night sky as faint streamers of stars extending from each galaxy. Some stars in these tails have been pulled so far from their parent galaxies that they're essentially in intergalactic space, wandering the void between the galaxies. At this point, the outer edges of the two galaxies are beginning to overlap. The outermost stars and gas clouds from each galaxy are now occupying the same region of space. This is first contact, the moment when we can definitively say the collision has begun. Let's pause here and consider what's happening to Earth at this point. 4 billion years is an enormously long time, and a lot can happen to a planet in that span. In fact, Earth's fate during the collision is intimately tied to what's happening with the Sun, because the Sun is evolving too. Following an inexorable path determined by the physics of nuclear fusion in its core. Our Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. Main sequence stars, and the Sun is a textbook example, burn hydrogen in their cores, fusing 4 hydrogen nuclei together to create one helium nucleus. This process releases energy according to Einstein's famous equation E equals mc squared. A tiny bit of mass gets converted into a tremendous amount of energy. The Sun converts roughly 600 million tons of hydrogen into helium every single second. In the process, about 4 million tons of mass get converted into pure energy. That energy, in the form of photons, gamma rays initially, gradually works its way from the core to the surface through a million-year journey of absorption and re-emission, and finally escapes into space as the sunlight that reaches Earth. This process has been going on steadily for 4.6 billion years, and it will continue for billions more. But it's not constant. As the Sun ages, subtle changes occur that have profound consequences. Here's what happens. As hydrogen fuses into helium in the core accumulates helium ash, the products of fusion. This helium doesn't participate in the hydrogen fusion reactions, it just sits there, inert, taking up space in the core. As more and more helium accumulates, the hydrogen fusion zone gradually migrates outward into regions that still contain fresh hydrogen. Meanwhile, the core slowly contracts under its own weight. Gravity is always trying to make the Sun collapse, and only the outward pressure from fusion energy production prevents this collapse. As the core contracts, it heats up. Higher temperatures mean faster fusion reactions in the surrounding hydrogen shell. More energy production means the Sun's outer layers expand, and the Sun's luminosity, its total energy output, gradually increases. This process is slow but relentless. Every billion years, the Sun's luminosity increases by roughly 10%. When the Sun first formed 4.6 billion years ago, it was about 70% as luminous as it is today. Earth received correspondingly less solar energy, which probably contributed to the snowball Earth episodes in Earth's early history, though the details are still debated. 4 billion years from now, when Andromeda arrives, the Sun will be roughly 40% more luminous than it is today. Some estimates suggest the increase could be even larger, perhaps 50 or 60%, depending on details of the Sun's internal structure that aren't perfectly known. That might not sound like much, but it has enormous consequences for Earth. The amount of energy Earth receives from the Sun determines Earth's climate. More solar energy means higher temperatures. Right now, Earth's climate is in a delicate balance. Energy comes in as sunlight, gets absorbed by the surface and atmosphere, and radiates back out as infrared heat. The atmosphere, particularly greenhouse gases like carbon dioxide and water vapor, trap some of this outgoing heat, keeping Earth warmer than it would be otherwise. This is the greenhouse effect, and it's what makes Earth habitable. Without it, Earth's average temperature would be well below freezing, but there's a limit to how much the system can adjust. As the Sun gets brighter and Earth receives more energy, temperatures rise. Higher temperatures cause more water to evaporate from the oceans. Water vapor is itself a greenhouse gas, so more water vapor means more greenhouse warming. That causes even more evaporation, creating a runaway feedback loop. Eventually, perhaps a billion years from now, maybe sooner, this runaway greenhouse will make Earth's surface too hot for liquid water to exist. The oceans will begin to evaporate. Water vapor will rise high into the atmosphere, where ultraviolet light from the Sun can split the water molecules apart. The hydrogen, being very light, will escape into space. The oxygen will react with rocks on the surface, forming minerals. Over hundreds of millions of years, Earth will lose its oceans entirely. The surface will be dry, hot, probably reaching temperatures of several hundred degrees. Any life that still exists will be confined to the deep subsurface, perhaps in pockets of water trapped in rocks miles below the surface, or in extreme environments near the poles where temperatures might still occasionally drop below the boiling point of water. Complex life, anything multicellular, will almost certainly be extinct long before this. The fossil record shows that life on Earth's surface requires liquid water, stable temperatures, and a protective atmosphere. As the oceans evaporate and temperatures rise, these conditions will disappear. Photosynthetic organisms, which form the base of Earth's food chain, will fail as CO2 levels drop too low. You see, plants need CO2 for photosynthesis, but they also need water. As the planet heats up, plants will close their stomata, the pores through which they absorb CO2, to prevent water loss. But closing stomata means less CO2 absorption, which means less photosynthesis. Eventually, plants won't be able to survive, and without plants, the entire ecosystem collapses. This could happen within the next 500 million to 1 billion years, though estimates vary widely. Some researchers think complex life might survive a bit longer, others think it could end sooner. But everyone agrees that by 2 billion years from now, Earth's surface will be uninhabitable. By 4 billion years from now, when Andromeda arrives, Earth will have been a lifeless, waterless desert for billions of years. The surface will be blasted by intense solar radiation. Any remaining atmosphere will be thin, perhaps mostly nitrogen and CO2, with no oxygen because there's no life producing it. And the sun's evolution is just getting started. Within another billion years after that, roughly 5 billion years from today, the sun will begin its transformation into a red giant. This transformation occurs when the core finally runs out of hydrogen entirely. At that point, hydrogen fusion ceases in the core. Without fusion to provide outward pressure, the core contracts rapidly. This contraction releases gravitational potential energy, heating the core to even higher temperatures. The temperature gets high enough that hydrogen fusion ignites in a shell surrounding the inert helium core. This shell fusion produces more energy than the original core fusion did. The enormous energy output causes the sun's outer layers to expand dramatically. The sun will swell to perhaps 200 or 250 times its current diameter, maybe more. Its surface will cool because the same amount of energy is now being radiated from a much larger surface area, so the sun will turn red, hence the name red giant. But its total luminosity will increase by a factor of 100 or more, potentially reaching 1,000 times its current luminosity. At its maximum size, the sun might extend to roughly 1 astronomical unit, the current distance from the sun to Earth. Mercury will definitely be swallowed. Venus will definitely be swallowed. Earth might just barely avoid being engulfed, or it might be swallowed too, depending on exactly how large the sun becomes and how much mass it loses during the expansion. You see, as the sun expands, it also loses mass. The outer layers are so loosely bound that solar wind and radiation pressure blow them away into space. The sun might lose 30% or more of its mass during the red giant phase. As the sun loses mass, its gravitational hold on the planets weakens. The planet's orbits expand outward. Earth might migrate outward fast enough to stay ahead of the expanding solar surface. Current best estimates suggest Earth will probably not be swallowed, but it will come very close, with the sun's surface passing perhaps within a few 100,000 miles of Earth's orbit. But even if Earth avoids being physically engulfed, it won't survive in any meaningful sense. At the sun's closest approach, Earth will be subjected to temperatures of several thousand degrees. The surface will melt. Rock will vaporize. Any remaining atmosphere will be blown away by the intense radiation and solar wind. If any remnant of Earth survives, it will be a charred, airless cinder, a lump of rock and metal stripped of everything that once made it interesting. During this red giant phase, which lasts several 100 million years, something interesting happens to the outer solar system. Because the sun is now so much more luminous, the habitable zone, the region where temperatures are right for liquid water, moves outward. Jupiter and Saturn are still too far away to benefit much, but their moons might. Europa, one of Jupiter's moons, currently has a thick ice crust overlying an ocean of liquid water. We know the ocean exists because of gravitational measurements and observations of the surface indicating ice flows. During the red giant phase, Europa's ice might melt entirely, creating a global ocean exposed to space. Titan, Saturn's largest moon, currently has a thick atmosphere and lakes of liquid methane on its surface. The surface temperature is around -290 degrees Fahrenheit, far too cold for liquid water. But as the sun expands and brightens, Titan will warm up. The methane will evaporate, the thick atmosphere might be partially blown away, and water ice will melt. Titan might briefly have liquid water oceans on its surface. This represents a temporary window of habitability, perhaps lasting a few 100 million years. It's conceivable that life could arise in these newly warmed environments, though it would require either that life already existed there, in subsurface oceans, and simply expanded to the surface, or that it arose extremely quickly from scratch. But this would be temporary. After the red giant phase, the sun will shed its outer layers entirely, creating a beautiful planetary nebula, a glowing shell of gas expanding into space. And what remains at the center will be the hot, dense core, now called a white dwarf. The white dwarf will be about the size of Earth, roughly 8,000 miles in diameter, but will contain roughly half the sun's original mass. This makes it incredibly dense, roughly 1,000,000 times denser than water. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf will be extremely hot at first, with surface temperatures reaching 100,000 degrees or more. But it has no energy source, no fusion occurring in its interior, so it will simply radiate its stored thermal energy into space and gradually cool. Over billions of years, trillions of years, eventually it will cool to a black dwarf, a lump of carbon and oxygen no longer emitting any significant heat or light. But that takes longer than the current age of the universe, so all white dwarfs that exist today, including the future white dwarf sun, are still hot. After the sun becomes a white dwarf, roughly 5 billion to 6 billion years from now, the solar system will be a very different place. The inner planets, Mercury, Venus, and possibly Earth, will be gone, either swallowed or vaporized. What remains are the outer planets, Jupiter, Saturn, Uranus, Neptune, along with their moons and the Kuiper Belt and Oort cloud objects. These will still orbit the white dwarf sun, though their orbits will have expanded somewhat due to the sun's mass loss. The white dwarf will still emit heat and light, though much less than the sun does today. The outer planets will cool dramatically. Any temporarily habitable moons will freeze solid again, their brief window of warmth closed forever. And throughout all of this, the galaxy merger will be well underway. The sun, or rather the white dwarf that it becomes, will have its orbit scrambled by the gravitational chaos of the merger. The ordered circular orbit we currently follow will be replaced by something more elliptical, more randomly oriented. We might end up closer to the galactic center, in a denser region with more stars, or we might end up farther out, in a sparser region. We might even end up in a completely different part of the merged galaxy, hundreds of thousands of light years from where we started. There's also a possibility, small but real, that the sun could be ejected from the galaxy entirely. During the chaotic interactions of the merger, some stars get gravitational kicks powerful enough to exceed the galaxy's escape velocity. These stars become intergalactic travelers, wandering the void between galaxies. If the sun gets ejected, the entire solar system goes with it. The planets, moons, asteroids, and comets are all bound to the sun much more tightly than the sun is bound to the galaxy, so everything stays together. But now we're drifting through intergalactic space. From the outer planets, if any observers exist there, the night sky would be incredibly dark. The white dwarf sun would still shine, still providing some light, but the stars would be gone. The galaxy, now distant, would appear as a bright smudge, a fuzzy patch of light containing the combined glow of 1 trillion stars, but there would be no individual stars visible, no constellations, no Milky Way band. Just darkness, profound and absolute. Now, back to the collision itself. 4 billion years from now, Andromeda dominates the sky, and the outer edges of the two galaxies are about to overlap. This is first contact, the moment when stars from one galaxy actually enter the space occupied by the other galaxy. It's not a sharp boundary. Galaxies don't have defined edges like a solid object. They gradually fade out, becoming less and less dense until you can't really say where the galaxy ends and intergalactic space begins. But there's definitely a point where you can say the galaxies are now occupying the same space, and that's what's happening now. From Earth, assuming anyone is watching, the night sky would be absolutely spectacular. Instead of the faint Milky Way band we see today, you'd see two distinct structures crossing the sky. One would be the remaining core of the Milky Way, still recognizable but distorted. The other would be Andromeda's core, now so close that individual bright stars within it would be visible. Between the two cores, you'd see chaos. Stars from both galaxies mixed together, creating a complex, turbulent structure. Bright blue regions of star formation would dot the sky, glowing clouds where gas clouds have collided and ignited into new stars. And threading through everything would be dark lanes of dust, silhouetted against the background glow. But here's the remarkable thing. If you were standing on Earth at this moment, assuming Earth is still habitable, which it almost certainly isn't, you probably wouldn't notice anything unusual in your daily life. The sun would still rise and set. The seasons would still change if there were seasons. Life, if any existed, would continue. That's because even though the galaxies are colliding, the distances between individual stars are still enormous. The nearest stars from Andromeda might be many light years away. There's no immediate danger of a collision with another star, no radiation surge, no gravitational disruption of Earth's orbit, just a slowly changing night sky. However, the galaxy as a whole is beginning to feel the effects. The sun's orbit around the galactic center, which has been stable for billions of years, is now changing. Andromeda's gravity is pulling on everything in the Milky Way, and the result is that stellar orbits are becoming more chaotic. Some stars are being pulled toward Andromeda. Others are being flung outward, away from both galaxies. And some, including possibly the Sun, are having their orbits scrambled, sent into new paths that are more elliptical, more tilted, or more erratic than before. This orbital scrambling is one of the main effects of a galaxy merger. Before the collision, most stars in a spiral galaxy follow fairly circular orbits around the galactic center, all moving in roughly the same plane. This organized motion is what creates and maintains the spiral structure. But when you add the gravitational influence of another galaxy, that organization breaks down. Stars get kicked into new orbits that are more random, more three-dimensional. The gas clouds between the stars are affected even more dramatically. Unlike stars, which are basically point masses moving through space, gas clouds are extended structures that can collide with each other. When gas clouds from the Milky Way collide with gas clouds from Andromeda, they crash together at relative velocities of hundreds of thousands of miles per hour. The kinetic energy of this collision gets converted into heat. The gas heats up to millions of degrees, glowing in X-rays and ultraviolet light. But something else happens too. The collision compresses the gas. And when gas gets compressed, it can collapse under its own gravity if it reaches high enough density. This collapse forms new stars, lots of them. This is the starburst we mentioned earlier, and it's one of the most dramatic effects of the collision. Over the next few 100 million years, millions upon millions of new stars will form in the regions where gas clouds collide. These newborn stars are massive and hot, tens or hundreds of times the mass of the Sun. They burn through their fuel incredibly quickly, living only a few million years before exploding as supernovae. So the galaxy merger triggers not just star formation, but also a dramatic increase in the supernova rate. Now, supernovae are powerful events. A single supernova can briefly outshine its entire galaxy, releasing as much energy in a few weeks as the Sun will emit over its entire 10 billion-year lifetime. And supernovae don't just produce light, they produce high-energy radiation, cosmic rays, energetic particles traveling at nearly the speed of light. If you're anywhere near a supernova when it explodes, within maybe 100 light-years or so, the radiation can be dangerous. It could strip away a planet's ozone layer, exposing the surface to harmful ultraviolet light. It could cause mutations in any life that exists. It could potentially trigger mass extinctions. During the starburst phase of the merger, the supernova rate increases by orders of magnitude. Instead of 1 or 2 supernovae per century, which is typical for a normal galaxy, you might have dozens or hundreds per century. Any planets in the wrong place at the wrong time could be bathed in radiation. This is another reason why life during the merger would be challenging, even if your planet's orbit remains stable. Let's jump forward in time now. We're now roughly 4.5 billion years from today. The galaxies have been overlapping for about 500 million years. The two galactic cores, the dense central regions containing most of the mass, are approaching each other for the first time. This is called the first core passage, and it's one of the most dramatic moments of the entire merger. The galactic cores are incredibly dense regions. The density of stars near the Milky Way's center is thousands of times higher than the density out here in our neighborhood. And when two galactic centers pass through each other, you temporarily have double the density. This creates opportunities for close encounters between stars. While direct collisions are still rare, stars can pass close enough to each other that their gravitational influence becomes significant. A star might have its orbit drastically altered by a close pass with another star, or if a star has planets, those planets might be disturbed or even stripped away by the gravity of a passing star. For our solar system, this is one of the most dangerous moments of the entire merger. If we're unlucky enough to be near the core during this passage, there's a small but real chance that a close encounter with another star could disrupt the orbits of the planets. Jupiter might be knocked into a different orbit. Earth, if it still exists, might be pushed closer to the Sun or farther away. In a worst-case scenario, planets could be ejected from the solar system entirely, sent wandering into interstellar space as rogue planets. But let's put that risk in perspective. Even in the dense environment near the galactic core, the chances of any individual star having a disruptive close encounter are pretty low. Most stars, including probably the Sun, will pass through this period without any direct interactions. The distances are still just too large. What's more likely to affect us is the indirect effects. The gravitational chaos of the merger will send ripples through the entire galaxy. These ripples can disturb the orbits of everything, not just stars, but also gas clouds and the dark matter that makes up most of the galaxy's mass. And these disturbances can trigger events far from the core. The density of the galactic core during this passage would be something to behold. If you could somehow watch from a safe distance, you'd see two bright, compact regions of stars approaching each other, each surrounded by a haze of gas and dust. As they pass through each other, the gravitational interactions would cause the gas to heat up dramatically, glowing in X-rays and ultraviolet light. Some of this gas would fall toward the supermassive black holes, feeding them and causing them to become temporarily more active. When a black hole feeds, it doesn't just swallow material silently. The infalling matter forms an accretion disk, a swirling disk of superheated gas orbiting the black hole at nearly the speed of light. This disk can outshine the entire galaxy, radiating enormous amounts of energy. If both black holes become active during the core passage, the centers of both galaxies would light up brilliantly. From a distance, you'd see two intensely bright points of light, like cosmic headlights rushing toward each other. This would be a spectacular sight for any observers in nearby galaxies. Now, let's talk about what happens to the supermassive black holes. This is one of the most fascinating parts of the merger, and it's something astronomers are intensely interested in. When the two galactic cores pass through each other for the first time, the black holes don't immediately merge. They're still separated by thousands of light years, maybe more. But as the galaxies swing back together for subsequent passages, the black holes get closer and closer. Eventually, after multiple passages over hundreds of millions of years, they end up orbiting each other. Two supermassive black holes, one weighing 4 million solar masses and the other weighing perhaps 100 million to 200 million solar masses, circling around their common center of mass. This is called a binary black hole system, and it's an incredibly powerful source of gravitational waves. Gravitational waves are ripples in space-time itself, created by accelerating massive objects. They were predicted by Einstein over a century ago, but weren't directly detected until 2015. Since then, we've detected gravitational waves from dozens of black hole mergers, but all of them involved stellar mass black holes, the kind that form when massive stars die. We haven't yet detected the merger of two supermassive black holes, but we know it must happen during galaxy mergers. When Sagittarius A star and Andromeda's black hole orbit each other closely, they'll emit gravitational waves at a low frequency, lower than what our current detectors can sense. Future space-based detectors should be able to detect these waves. Any sufficiently advanced civilization in the local group would be able to observe this event in gravitational waves, watching as the two black holes spiral together. The orbital period gets shorter and shorter as the black holes lose energy to gravitational waves. They might orbit each other for millions of years, but eventually they get close enough that the orbital period drops to hours, then minutes, then seconds. And then, finally, they merge. The merger itself happens incredibly quickly. Two black holes orbiting each other at a significant fraction of the speed of light suddenly combine into a single larger black hole. The new black hole will weigh roughly 104 million to 204 million solar masses, the sum of the two original black holes. In the process, some mass gets converted directly into energy in the form of gravitational waves. The amount of energy released is staggering. In just a few seconds, the merger releases more energy than all the stars in both galaxies combined will emit over millions of years. It's the most powerful event in the universe, except for the Big Bang itself. But here's the thing, that energy is emitted as gravitational waves, not light. So unless you have a gravitational wave detector, you won't see anything. The night sky won't suddenly light up. There won't be a visible explosion. The black holes will quietly merge, shaking the fabric of space-time but not creating any visible display. After the merger, the new black hole will likely receive a kick, a recoil effect from the asymmetric emission of gravitational waves. This kick can be powerful enough to send the black hole moving through the galaxy at hundreds or even thousands of miles per second. Eventually, it will settle down at the center of the new merged galaxy, but for a while, it might wander. This wandering supermassive black hole is another potential hazard. The chances of it coming anywhere near any individual star system are vanishingly small, but if it did pass close to a star, it would be catastrophic. The black hole's immense gravity would tear the star apart, creating a spectacular tidal disruption event that would briefly outshine the entire galaxy. The kick velocity depends on the spins and masses of the two black holes. If they're spinning in the same direction and their spins are aligned, the kick is relatively small. If they're spinning in opposite directions or at odd angles, the kick can be much larger. Computer simulations suggest kicks of up to several thousand miles per second are possible. A black hole moving at these speeds would take millions of years to slow down and settle at the galactic center. During this time, it would plow through the galaxy, occasionally encountering stars and gas clouds. Any star that came too close would be captured or disrupted, adding to the black hole's mass. Let's get into the details of what happens to individual stellar systems during the merger. We've said that direct collisions between stars are rare, but close encounters can still have dramatic effects. Imagine two stars passing within a few light weeks of each other. That's close by cosmic standards, but still far enough that the stars don't physically touch. As they approach, their gravitational fields interact. Each star tugs on the other, altering its trajectory. It's similar to what happens when two billiard balls collide, except the stars don't physically touch. They interact through gravity alone, and the encounter happens over months or years as the stars approach, reach their closest point, and then recede. The outcome of a stellar encounter depends on several factors: how close the stars get, how fast they're moving relative to each other, and their masses. If two stars pass within a few light weeks of each other while moving at typical galactic velocities, which are hundreds of thousands of miles per hour, they'll exchange some energy and momentum. One star might be sped up slightly while the other is slowed down. Their directions of motion will change, bending their paths through space. This is called gravitational deflection, and it's the primary mechanism by which stars' orbits get randomized during a galaxy merger. Now, if the stars happen to be moving slowly relative to each other and they pass very close, something more interesting can happen. They might temporarily become gravitationally bound to each other, forming a binary star system. This would be a loose binary, with the two stars orbiting each other at a distance of light months or light years. But it would be stable over millions of years. However, if a third star comes along and interacts with this binary, the system becomes unstable. Three-body gravitational interactions are chaotic and unpredictable. The most common outcome is that one star gets ejected at high speed, becoming what's called a hypervelocity star, while the other two form a tighter binary. This process, called binary hardening through three-body interactions, is one way that close binary star systems form. Hypervelocity stars are fascinating objects. These are stars moving so fast that they can escape the galaxy's gravity entirely. They've been accelerated to speeds of hundreds or even thousands of miles per second, fast enough to reach escape velocity. We've detected several hypervelocity stars in the Milky Way, and they're thought to be created by interactions with the supermassive black hole at the galactic center, or by binary interactions in dense stellar environments. During the merger, the creation of hypervelocity stars will increase dramatically. Close encounters between stars will be more common, especially during the core passages. Some of these encounters will result in stars being flung out of the galaxy at enormous speeds. These stars, along with any planets they might have, will become intergalactic travelers, leaving the merged galaxy entirely and heading out into the void between galaxies. There's also the question of what happens to existing binary star systems during the merger. Many stars are already in binary or multiple star systems, orbiting each other in stable configurations. During a close encounter with a third star, these systems can be disrupted. The intruder star might pull one component away from the binary, breaking it apart, or it might join the system, creating a triple star system. Triple star systems are less stable than binaries and often undergo complex gravitational interactions that eventually result in one star being ejected. Now, what about planetary systems? If a star has planets, what happens to them during the merger? In most cases, probably nothing. The planets are bound to their star much more strongly than the star is bound to the galaxy. It would take a very close encounter with another star to disrupt a planetary system. But close encounters do happen, especially during the core passages. Let's imagine a scenario where another star passes within about half a light year of the Sun. That's roughly 3 trillion miles. Far enough that there's no danger of collision, but close enough that gravitational effects become significant. The outer planets, especially those on the outskirts of the solar system or any objects in the Oort cloud, might be affected. A passing star's gravity could perturb their orbits, making them more elliptical or even ejecting them entirely from the solar system. The inner planets, if they still exist at this point, would probably be safe. They're closer to the Sun and more tightly bound. It would take a much closer pass to disrupt their orbits. But there's another effect to consider. The Oort cloud, that vast spherical shell of comets surrounding the solar system at a distance of roughly 1 light year, is only very loosely bound to the Sun. A passing star could easily disturb the Oort cloud, sending comets into the inner solar system. This could trigger a period of increased comet impacts on the planets. We've actually seen this happen in our own history. There's some evidence that close encounters with other stars in the past have disturbed the Oort cloud and triggered comet showers that resulted in impact events on Earth. During the merger, these encounters would be more common. The merger might also create planetary systems with very different architectures from what we're used to. During close stellar encounters, while complete disruption is rare, subtle gravitational perturbations can occur. A planet on an initially circular orbit might be nudged into a more elliptical orbit. Multiple planets in a system might have their orbital resonances disrupted, leading to instabilities that play out over millions of years. Some planetary systems might even capture planets from other systems during close encounters. Imagine 2 stars passing within half a light year of each other. A planet on a wide orbit around one star might be pulled away by the gravity of the other star, switching allegiance mid-flight. This would create planetary systems with a mix of planets from different origins, possibly with very different compositions and histories. During the merger, the chaotic gravitational environment will likely create many rogue planets. A close encounter between 2 stars might eject planets from one or both systems. These planets become interstellar wanderers, drifting through the galaxy on their own. Some estimates suggest there might already be as many rogue planets as there are stars, and the merger could substantially increase this population. For any life on a rogue planet, assuming life could exist in such a cold, dark environment, the merger would be an interesting time. The planet would pass through regions of increased stellar density, occasionally coming close to stars or other planets. There might even be rare occasions when a rogue planet gets captured by a new star, joining a new planetary system entirely different from the one it was born in. Let's also think about what happens in different regions of the galaxies during the merger. The experience of a star system will depend heavily on where it's located. Stars in the central regions, near the galactic cores, will experience the most dramatic effect. The density is highest there, so close encounters are most likely. The gravitational chaos is most intense. The starburst is most active. The supernova rate is highest. A planetary system in the central regions would face significant hazards. Close encounters with other stars could disrupt planetary orbits. Supernova explosions could bathe the system in harmful radiation. The intense star formation would create a bright, energetic environment with lots of ultraviolet light and X-rays. Stars in the outer regions, far from the cores, will have a much calmer experience. The density is lower, so close encounters are less likely. The gravitational effects are more subtle, The starburst is less intense. A planetary system in the outer regions might barely notice the merger is happening, at least in terms of immediate local effects. The main change would be the night sky, which would gradually become more complex and chaotic as the galaxies interpenetrate. Stars in the disk, the flat part of the galaxy between the core and the outer halo, will have an intermediate experience. Some disk regions will experience intense star formation as gas clouds collide. Other disk regions, away from the main collision zones, will be relatively calm. The fate of any individual star system is somewhat random, depending on the details of its orbit and the chance encounters it has with other stars. But statistically, most stars will survive the merger without any catastrophic encounters. Most planetary systems will survive with their planets still in roughly their original orbits. The main change for most star systems will be the new galactic environment they find themselves in after the merger. Instead of a neat spiral galaxy with organized rotation, they'll be in an elliptical galaxy with random stellar motions. Instead of being part of a thin disk, they might be part of a thick spheroid. Instead of orbiting in a relatively uncrowded region, they might find themselves in a denser or sparser region than before. After the first core passage, the two galaxies don't just stick together. They're moving too fast for that. Instead, they swing past each other, pulled apart by their own momentum, and then gradually slow down and swing back together for a second pass. This happens because they haven't lost enough energy yet. During the first passage, some energy is transferred between the stars through gravitational interactions. Some stars are sped up, others are slowed down. This energy exchange acts like friction, gradually removing energy from the orbital motion of the two galaxies. But it's not enough to make them merge immediately. So the galaxies separate again, their cores moving apart to a distance of hundreds of thousands of light years. Then gravity pulls them back together for a second passage, then a third, then a fourth. Each time, they lose more energy. Each time, they don't separate quite as far. Eventually, after maybe 5 or 6 passages over 1 billion years or so, they lose enough energy that they can't separate anymore. The cores merge permanently, forming a single galactic core. During all of this, the structure of both galaxies is being completely destroyed. The neat spiral arms that characterized both the Milky Way and Andromeda are gone, torn apart by tidal forces and gravitational interactions. The organized rotation that maintained those spiral arms has been replaced by chaotic, random motions. Stars that were moving in orderly circular orbits are now moving in elliptical orbits with random orientations. The result is that the merged galaxy no longer looks like a spiral. It looks like what astronomers call an elliptical galaxy. Elliptical galaxies are shaped like elongated spheres or footballs. They don't have spiral arms or disks. They don't have much gas left because most of it was used up in the starburst. They're dominated by old red stars moving in random orbits. This is the final product of the merger. A giant elliptical galaxy, probably about 200,000 to 300,000 light-years across, containing the combined stars from both the Milky Way and Andromeda. Astronomers have already given this future galaxy a name, Milcomeda, or sometimes Milcdromeda. Milcomeda will be one of the largest galaxies in the local group. It will contain roughly 1.2 trillion stars, maybe more, and it will look completely different from either of its parent galaxies. No spiral arms, no disk, just a vast, roughly spherical collection of stars. Let's talk more about what Milcomeda will actually look like and how it will function as a galaxy. From the outside, if you could view Milcomeda from another galaxy, you'd see a bright, roughly elliptical blob of light. The core would be very bright, containing a dense concentration of stars and the merged supermassive black hole. Moving outward from the core, the brightness would gradually fade as the stellar density decreases. The color of Milcomeda would be different from its parent galaxies. Spiral galaxies like the Milky Way and Andromeda have a mix of blue regions where young hot stars are forming and redder regions where older, cooler stars dominate. Elliptical galaxies tend to be redder overall because they've used up most of their gas in starbursts and have little ongoing star formation. By the time Milcomeda forms, perhaps 6 or 7 billion years from now, the starburst will be mostly over. The gas will have been consumed or blown away by supernova winds. What remains are the stars that formed during the merger, plus all the stars that existed before. The young, massive stars from the starburst will have died, many of them exploding as supernovae. What remains from the starburst are the longer-lived stars, those with masses similar to the Sun or smaller. These stars will still be shining billions of years after the merger, gradually aging and cooling. Most of the stars in Milcomeda will be old, red stars. The original stars from the Milky Way and Andromeda will be even older than they are today, many of them red giants or white dwarfs. The merger-era stars will be middle-aged, similar to what the Sun is today. And there will be very few young blue stars because there's little gas left to form new stars. This gives Milcomeda its reddish color, the characteristic color of elliptical galaxies. The structure of Milcomeda will be very different from a spiral galaxy. Instead of a thin disk with spiral arms, Milcomeda will have a thick, three-dimensional distribution of stars. Stars will move in all directions, on orbits with random orientations and eccentricities. Some stars will have nearly circular orbits. Others will have highly elliptical orbits that take them from the core to the outer regions and back. Some will orbit in one plane, others in perpendicular planes. There's no overall rotation like there is in a spiral galaxy. This random motion is a result of the gravitational interactions during the merger. All that scrambling and kicking of stellar orbits results in a system where orbits are thoroughly mixed. At the very center of Milcomeda will sit the merged supermassive black hole, weighing perhaps 100 million to 200 million solar masses. Surrounding the black hole will be a dense stellar core, a region where stars are packed thousands or even tens of thousands of times more densely than they are in our current neighborhood. In this core region, the night sky from any planet would be spectacular. Thousands of stars would be visible to the naked eye. The brighter stars would cast noticeable shadows. The combined light from all these stars would create a permanent twilight, even during the night. True darkness would be almost impossible to find. But this dense environment also comes with hazards. Close encounters between stars would be more common in the core. While still rare in absolute terms, the frequency would be much higher than in the outskirts. Any planetary systems in the core would face increased risk of disruption over time. The supernova rate would also be higher in the core, at least for a while after the merger. The starburst creates many massive stars that live fast and die young. Even after the starburst ends, these stars will continue exploding for millions of years. The core regions would be bathed in supernova radiation more frequently than the outskirts. Moving outward from the core, the density gradually decreases. In the middle regions of Milcomeda, perhaps 50,000 to 100,000 light-years from the center, the stellar density would be more comparable to what we experience today. Stars would be separated by light-years, close encounters would be rare, and the night sky would look more like what we're used to. Farther out, in the outer halo of Milcomeda, perhaps 200,000 light-years or more from the center, the stellar density would be very low. Stars would be separated by tens of light-years. The night sky would be dark, with relatively few stars visible. The galactic core would appear as a bright, fuzzy ball of light in the distance. Throughout Milcomeda, there would also be globular clusters. These are dense, roughly spherical collections of stars, typically containing hundreds of thousands or millions of stars in a volume just tens of light-years across. Both the Milky Way and Andromeda currently have populations of globular clusters orbiting them. After the merger, these globular clusters will still exist, now orbiting Milcomeda. Globular clusters are interesting because they contain some of the oldest stars in the universe. They formed early in the history of their parent galaxies, often more than 10 billion years ago. The stars in globular clusters are metal-poor, meaning they contain very little of the heavier elements beyond hydrogen and helium. This is because they formed before generations of stars had enriched the interstellar medium with heavier elements through supernova explosions. During the merger, some globular clusters might be disrupted by gravitational interactions. Others might survive intact, and new globular clusters might form during the merger from gas clouds that collapse under unusual conditions. Milcomeda will also contain remnants of the tidal tails. Remember those long streams of stars pulled out of each galaxy during the approach? Some of those stars will eventually fall back into Milcomeda, accreted over billions of years. Others will remain in the intergalactic space around Milcomeda, forming diffuse streams and shells of stars orbiting at great distances. These stellar streams are actually observable in elliptical galaxies today. Astronomers use them as fossil records, tracers of past merger events. By studying the positions and velocities of stars in these streams, we can reconstruct the history of the mergers that created the elliptical galaxy. Future astronomers living in Milcomeda billions of years from now could do the same. By studying stellar streams around their galaxy, they could piece together the history of the Milky Way-Andromeda merger, figuring out when it happened, how the galaxies approached each other, and what the resulting dynamics were. Now, let's talk more about dark matter, because we haven't discussed it in depth yet, and it plays a crucial role in the merger. We've mentioned that galaxies are embedded in halos of dark matter, but what exactly is dark matter, and how does it behave during the merger? Dark matter is one of the biggest mysteries in modern physics. We know it exists because we can see its gravitational effects, but we don't know what it's made of. It doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. The only way we know it's there is through gravity. Galaxies rotate faster than they should based on the visible matter alone. If you calculate the rotation curve of a galaxy, the speed at which stars orbit at different distances from the center, and you base that calculation only on the visible mass, the stars and gas, you find that the outer stars should be moving much slower than they actually are. They're moving so fast that they should fly off into space, not remain in orbit. The only explanation is that there's additional mass we can't see. This invisible mass provides the extra gravity needed to keep the outer stars in their orbits. That invisible mass is dark matter. Galaxy clusters show the same effect. The galaxies in a cluster are moving so fast that the cluster should fly apart unless there's much more mass than we can see. Again, dark matter provides the solution. Gravitational lensing provides even more direct evidence. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the massive object bends the light, acting like a lens. By measuring how much the light is bent, we can calculate how much mass is doing the bending. And consistently, we find much more mass than we can account for with visible matter. All of this evidence points to dark matter, making up roughly 85% of the total matter in the universe. Only 15% is normal matter, the atoms that make up stars, planets, and us. But what is dark matter made of? That's the mystery. It's not normal atoms, we know that. If it were, it would interact with light and we'd be able to see it. The leading hypothesis is that dark matter consists of some exotic particle that we haven't discovered yet. Maybe WIMPs, weakly interacting massive particles. Maybe axions. maybe something else entirely. Physicists have been searching for dark matter particles for decades, building sensitive detectors deep underground to shield them from cosmic rays, hoping to catch a dark matter particle interacting with normal matter. So far, no confirmed detection. But whatever dark matter is made of, we know it interacts through gravity, and that's all that matters for the galaxy merger. During the merger, the dark matter halos of the Milky Way and Andromeda will merge just like the visible parts of the galaxies. But the dark matter behaves differently from the stars and gas. Stars are discrete objects moving on ballistic trajectories. They respond to gravity but don't collide with each other. Gas clouds can collide. When gas clouds hit each other, they can lose energy through radiation, cooling down, and potentially collapsing to form stars. Dark matter is even more collisionless than stars. Dark matter particles pass right through each other without interacting. They don't collide, they don't lose energy through radiation. They just respond to gravity. This means that when the dark matter halos merge, they interpenetrate freely. Dark matter from the Milky Way passes through dark matter from Andromeda without any collisions or interactions beyond gravity. Computer simulations of galaxy mergers need to track the dark matter separately from the stars and gas because it behaves differently. The simulations show that after the merger, Milcomeda will be embedded in a roughly spherical halo of dark matter, extending perhaps 600,000 to 1 million light-years from the center. This dark matter halo will contain most of Milcomeda's mass, perhaps 85 to 90% of the total. The stars, gas, and everything we can see will account for only 10 to 15%. The dark matter determines the overall gravitational potential well in which the visible galaxy sits. It's like the scaffolding, the underlying structure. The visible matter falls into this gravitational well and settles into the distribution we observe. Understanding how dark matter behaves during mergers is crucial for understanding galaxy evolution. And astronomers can test their models of dark matter by comparing simulations to observations of real galaxy mergers. If dark matter behaves the way we think it does, simulations should match observations. And indeed, they do, at least to a good approximation. This gives us confidence that our understanding of dark matter, while incomplete, is on the right track. Now, let's ask a more philosophical question. If intelligent life still exists somewhere in the solar system, or in the galaxy generally during this time, what would it be like to live through the merger? First, remember that this entire process takes billions of years. No individual organism, not even an individual civilization in any recognizable form, would experience the whole thing. You'd need a continuous chain of civilizations, each one building on the knowledge of the previous, to maintain awareness of what's happening over such vast timescales. Or you'd need a civilization that achieves some form of extreme longevity, either biological or technological. Maybe they upload their minds into computers. Maybe they achieve functional immortality through advanced medicine. Maybe they become some form of post-biological intelligence. But let's imagine such a civilization exists. What would they observe? In the early stages, millions of years before first contact, they'd see Andromeda growing larger in the sky. Their astronomers would be able to predict the collision with increasing accuracy as observations accumulate. They'd map the approaching galaxy in detail, identify its structure, locate its supermassive black hole, estimate the timing of first contact. They'd have centuries or millennia of advanced warning, perhaps longer. This would give them time to prepare, to move populations if necessary, to build infrastructure that could withstand the changes. A sufficiently advanced spacefaring civilization could evacuate entire regions of the galaxy that were expected to be particularly affected. They could relocate populations to safer areas, perhaps the outer halo where stellar density is low and encounters are unlikely. They could build space habitats that aren't tied to any particular star, mobile habitats that can move between star systems as needed. This would give them flexibility to avoid dangerous regions and seek out opportunities. As the galaxies draw closer, they'd see the tidal distortions begin. Long streams of stars pulled from each galaxy would become visible. The rate of supernova explosions in both galaxies would increase as the starburst began. The night sky would gradually brighten and become more chaotic. They might even detect the gravitational waves from the merging supermassive black holes if they had advanced enough technology. Gravitational wave astronomy would give them a completely different view of the merger, revealing the dynamics of the supermassive black holes as they spiral together. During the actual core passages, assuming they had telescopes and sensors scattered throughout the region, they'd observe vast structures in motion, spiral arms being torn apart, gas clouds colliding and igniting into new star-forming regions, the galactic cores approaching each other, passing through, separating, and coming back together. It would be a spectacle on an unimaginable scale, playing out over millions of years but observable in its entirety through records, predictions, and multi-generational observation programs. But what about the dangers? Would a civilization living through the merger be in peril? The answer depends on where they are and what resources they have. If they're confined to a single planet, they're vulnerable. An increased rate of supernova explosions could bathe their planet in harmful radiation. A close encounter with another star could disrupt their planet's orbit or trigger comet impacts. Climate changes from varying stellar radiation could make their world uninhabitable. But if they're a spacefaring civilization with the ability to move between star systems or build habitats in space, they can avoid most of these dangers. They could simply relocate away from dangerous regions and move to safer areas. A civilization with true interstellar capability wouldn't be tied to any one location. They could ride out the merger by staying in the safest regions, moving as needed, and avoiding the most chaotic areas. In fact, a sufficiently advanced civilization might even benefit from the merger. The starburst creates millions of young, hot stars that could serve as energy sources. The gravitational chaos might scatter valuable resources, such as metal-rich asteroids or comets, throughout the galaxy, making them more accessible. New star systems are forming constantly during the starburst, offering opportunities for colonization. From this perspective, the merger isn't necessarily a disaster. It's a transformation, a change from one type of galaxy to another. Whether that's good or bad depends entirely on your perspective and capabilities. A primitive civilization confined to one planet would see the merger as an existential threat. An advanced spacefaring civilization would see it as a period of change, certainly, but not necessarily catastrophic. They might even view it as an opportunity, a chance to spread to new star systems, to harvest the energy of young hot stars, to explore the newly chaotic galactic environment. Let's also consider what happens even farther into the future, beyond the formation of Milcomeda. Milcomeda won't be the end of the story for our cosmic neighborhood. The local group contains other galaxies besides the Milky Way and Andromeda, and over time, these smaller galaxies will merge with Milcomeda too. The Triangulum Galaxy, the third largest member of the local group, might merge with Milcomeda. The timing is uncertain because Triangulum's orbit is complex and its exact trajectory isn't perfectly known, but computer simulations suggest it could merge with Milcomeda perhaps 1 billion or 2 billion years after the Milky Way-Andromeda merger. When Triangulum merges, it will add perhaps 40 billion to 50 billion more stars to Milcomeda. The merger will trigger another, smaller starburst as Triangulum's gas collides with any remaining gas in Milcomeda. More spiral structure will be destroyed, further randomizing stellar orbits. There are also dozens of dwarf galaxies orbiting both the Milky Way and Andromeda. These small galaxies, containing millions or billions of stars, are slowly falling toward their parent galaxies due to dynamical friction. This is a process where a massive object moving through a background of less massive objects gradually loses energy and slows down. The dwarf galaxies will gradually spiral inward and eventually be absorbed by Milcomeda. Each merger will add stars to Milcomeda and slightly perturb the orbits of existing stars. But because the dwarf galaxies are so small compared to Milcomeda, these mergers won't dramatically alter the overall structure. Over tens of billions of years, all the galaxies in the local group will eventually merge into a single giant galaxy. This is the ultimate fate of our cosmic neighborhood. Gravitationally bound structures merge over time unless something prevents it. But there's something else happening on an even larger scale that will profoundly affect Milcomeda's future. The universe is expanding. Space itself is stretching, carrying galaxies away from each other. This expansion was discovered by Edwin Hubble in the 1920 seconds. He observed that distant galaxies show redshifts in their spectra, indicating they're moving away from us. And the farther away a galaxy is, the faster it's receding. This led to the realization that the universe itself is expanding. It's not that galaxies are moving through space, it's that space itself is growing, stretching, carrying galaxies along with it. And not only is the universe expanding, but in 1998, astronomers discovered that the expansion is accelerating. Distant supernovae appeared dimmer than expected, suggesting the universe is expanding faster now than it was in the past. This acceleration is driven by something called dark energy, an even more mysterious component of the universe than dark matter. Dark energy acts like a kind of anti-gravity on cosmic scales. It doesn't push galaxies apart directly. Instead, it causes space itself to expand faster. We don't know what dark energy is. We don't know why it exists. We just know it's there because we can see its effects on the expansion of the universe. Current observations suggest that dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, everything we can see, accounts for only about 5%. The universe is dominated by components we don't understand, dark matter and dark energy. What does this mean for Milcomeda? On scales smaller than a few tens of millions of light-years, dark energy doesn't matter much. Gravitationally bound structures like galaxies and galaxy groups aren't torn apart by the accelerating expansion. Gravity within these structures is strong enough to overcome the expansion, but on larger scales, the accelerating expansion dominates. Galaxies and galaxy clusters that aren't gravitationally bound to each other are being carried apart by the expansion. And as time goes on, they're receding faster and faster. Eventually, trillions of years from now, galaxies outside the local group will recede so far and so fast that light from them can no longer reach us. They'll disappear beyond the cosmic horizon, the boundary beyond which light can't catch up to us because space is expanding too fast. At that point, any astronomers living in Milcomeda will look out and see only their own galaxy and perhaps a few nearby companions that merged with it. No other galaxies visible anywhere. No evidence that the universe contains anything beyond their cosmic island. They might conclude, based on their observations, that the universe consists of just one galaxy and nothing else. They'd be wrong, of course. The rest of the universe would still exist, billions of galaxies in every direction, but it would be forever beyond their ability to observe. This has profound implications. Future civilizations will have a fundamentally different view of the universe than we do. They won't see the cosmic web of galaxies. They won't see the large-scale structure of the universe. They won't be able to study distant galaxies to learn about the universe's history and evolution. We're living in a special time, cosmologically speaking. The universe is old enough that we can study its history, look back at the cosmic microwave background radiation from the Big Bang, observe distant galaxies as they were billions of years ago. But the universe is young enough that we can still see this vast cosmic structure. The billions of galaxies, the clusters and superclusters, the cosmic web. Future civilizations won't have this advantage. They'll live in an older, emptier-looking universe. This isn't just philosophical speculation. It has practical implications for astronomy and cosmology. If we lived in Milcomeda 100 trillion years from now, we might not be able to discover many of the things we know today. We couldn't measure the expansion of the universe by observing distant galaxies because there wouldn't be any visible distant galaxies. We couldn't study galaxy evolution across cosmic time. We couldn't observe the cosmic microwave background because it would have redshifted to undetectable wavelengths. Our knowledge of the universe depends on the cosmic time at which we exist. We're fortunate to live when we do, at a time when the universe is observable and comprehensible. But returning to Milcomeda specifically, what will its long-term future be? Over trillions of years, star formation in Milcomeda will gradually cease. The gas will all be used up, converted into stars, or expelled from the galaxy by supernova winds. Without gas, no new stars can form. The massive stars will die first, living only millions of years. Then stars like the Sun will die, lasting billions of years. Eventually, even the smallest red dwarf stars will exhaust their fuel, though this takes trillions of years. As stars die, some will explode as supernovae, creating neutron stars or black holes. Others will shed their outer layers and become white dwarfs. Over time, the galaxy will come to consist mostly of stellar remnants, white dwarfs, neutron stars, and black holes. These remnants don't shine like stars. White dwarfs gradually cool, becoming black dwarfs, cold lumps of carbon and oxygen. Neutron stars cool and fade. Black holes don't emit anything except Hawking radiation, and for stellar mass black holes, that's negligibly small. Milcomeda will gradually darken. Instead of a bright galaxy full of shining stars, it will become a dark galaxy full of stellar corpses. The few remaining stars, the longest-lived red dwarfs, will be scattered through a sea of darkness. The night sky from any planet in such a galaxy would be nearly black. Almost no stars visible. The galactic core, instead of being a bright region, would be dark, just a concentration of black holes and white dwarfs. But even this isn't the end. Over even longer timescales, perhaps 10 to the 20th power years, stellar remnants will occasionally collide or get ejected from the galaxy through multi-body gravitational interactions. The galaxy will gradually evaporate, losing stars to intergalactic space, and the supermassive black hole at the center will grow. Occasionally, stars or stellar remnants will fall into it, adding to its mass. Over tens of billions of years, the central black hole might grow to billions of solar masses. Eventually, perhaps after 10 to the 100th power years, even black holes will evaporate through Hawking radiation. Stephen Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. For stellar mass black holes, this radiation is incredibly weak, negligible compared to any other process. But over timescales of 10 to the 100th power years, even supermassive black holes will slowly evaporate. When the last black hole evaporates, Milcomeda will consist of nothing but photons, neutrinos, and whatever fundamental particles are stable over these timescales. The galaxy will have effectively dissolved into radiation. But these timescales are so long that they're almost meaningless. 10 to the 100th power years is a 1 followed by 100 zeros. The current age of the universe is only about 14 billion years. 4 times 10 to the 10th power. The timescale for black hole evaporation is 90 powers of 10 longer than the current age of the universe. For all practical purposes, Milcomeda will exist as a dark galaxy of stellar remnants for an almost incomprehensibly long time. Far, far longer than it exists as a bright galaxy of shining stars. But during its bright phase, during the trillions of years when stars still shine, Milcomeda will be home to whatever life exists in our cosmic neighborhood. If intelligence survives, if civilization persists, it will be in Milcomeda. If life spreads to the stars, it will spread through Milcomeda. If consciousness explores the cosmos, it will explore Milcomeda. This merged galaxy will be the future home for everything that descends from life on Earth or life anywhere else in the Milky Way or Andromeda. Now, let's address one final question. Is there anything we can do about the merger? Could a sufficiently advanced civilization prevent it or mitigate its effects? The short answer is probably not, at least not with any technology we can currently imagine. The merger is driven by the gravitational attraction between two enormous galaxies. The forces involved are so vast that they dwarf anything we can conceive of controlling. To prevent the merger, you'd need to either increase the angular momentum of the system so that the galaxies go into stable orbits instead of colliding, or remove energy from the system somehow to make the galaxies repel each other. Both of these would require manipulating the motion of trillions of stars across millions of light years. The energy required would be immense, far beyond anything we can currently imagine harnessing. Even a Kardashev Type 3 civilization, a hypothetical civilization capable of harnessing the energy of an entire galaxy, would struggle with this task. You'd need to be able to redirect the motion of individual stars on a galaxy-wide scale, which would require technology so advanced that it's essentially indistinguishable from magic. But perhaps the question itself is misguided. Maybe the merger shouldn't be prevented. After all, galaxy mergers have been happening throughout cosmic history, and they've led to the formation of new galaxies, new stars, new planetary systems. The universe doesn't care about our categories or our labels. The Milky Way is just a collection of stars, gas, and dark matter bound together by gravity. Milcomeda will be the same, just a different collection arranged in a different structure. What matters isn't preserving the Milky Way as it is today. What matters is ensuring that whatever life exists in the future can thrive, regardless of what the galaxy looks like. And for that, the key isn't preventing the merger. The key is adaptability. A civilization that can move between star systems, that isn't tied to any one planet or star, can survive and thrive regardless of what happens on galactic scales. In fact, the merger might even be beneficial in some ways. It creates new stars, new opportunities, new regions to explore and colonize. It's a transformation, not an ending. As we come to the end of our journey through this collision, let's reflect on what we've learned. We started by understanding the two galaxies involved, the Milky Way, our home, a barred spiral galaxy containing hundreds of billions of stars, and Andromeda, larger and more massive, containing 1 trillion stars. We learned how astronomers discovered that these two galaxies are on a collision course using Doppler shift measurements and proper motion observations to determine their velocities and predict the timing. We walked through the merger itself, step by step, the gradual approach over billions of years, the formation of tidal tails as gravitational forces stretch both galaxies, the first contact as the outer edges overlap, the dramatic core passages as the dense central regions pass through each other, the starburst triggered by colliding gas clouds, the eventual merger of the supermassive black holes, and the final result, Milcomeda, a giant elliptical galaxy. We explored what this means for individual stars and planetary systems, how the Sun's orbit will be scrambled, how Earth will likely be uninhabitable long before the merger due to the Sun's evolution. How close encounters between stars, while rare, can disrupt planetary systems, and how the merger creates hypervelocity stars and rogue planets. We discussed the role of dark matter, the invisible scaffolding that makes up most of both galaxies and shapes how the merger proceeds. And we thought about what it might be like to live through the merger, the dangers and opportunities it presents, and how a sufficiently advanced civilization might adapt. Finally, we looked even farther into the future, to the ultimate fate of the local group, and the eventual isolation of Milcomeda, as the accelerating expansion of the universe carries distant galaxies beyond the cosmic horizon. The merger of the Milky Way and Andromeda is one of the most significant events in the future history of our cosmic neighborhood. It's a transformation on a scale so vast that it's difficult to comprehend, playing out over billions of years, reshaping hundreds of billions of stars, and creating a galaxy fundamentally different from either of its parents. And yet, for all its cosmic grandeur, it's also a story about the impermanence of the structures we see around us. The galaxies we observe today, including our own, are not eternal. They're temporary configurations of matter, held together by gravity, evolving and changing over cosmic timescales. The universe is dynamic, not static. It's evolving, transforming, constantly creating new structures while destroying old ones. And we're living in one moment of that vast cosmic story, able to look both backward at the universe's history and forward to its future. The collision with Andromeda is billions of years away. It won't affect anyone alive today or for countless generations to come, but knowing about it, understanding it, gives us a deeper appreciation for our place in the cosmos. We're not living in an unchanging universe. We're living in a universe that has a past and a future, where galaxies collide and merge, where stars are born and die, where structures form and dissolve. And that story, that epic tale of cosmic evolution spanning billions of years, is the story we've told tonight. The story of two galaxies on a collision course, of the transformation they'll undergo, of the new galaxy that will emerge. It's a story that reminds us how vast the universe is, how long the timescales are, and how small but precious our moment in that vast cosmic history really is. Thanks for staying with me through this long journey across space and time. The final hour of the collision may be billions of years away, but in cosmic terms, it's just around the corner. And when it finally arrives, when Andromeda's trillion stars meet the Milky Way's hundreds of billions, it will be one of the most spectacular transformations our corner of the universe has ever seen.